This is my public lecture review of IMU on a chip, MEMS, and CMOS microsystems. The main idea of this lecture was the concept of CMOS and MEMS, which is the way to do sensing and data collection on a silicon chip. The MEMS is the sensor, and there are all different types of sensors, from temperature to pressure to voltage. And then the CMOS is the silicon that processes those signals and can turn it into a digital form for an understanding for the rest of the chip and make more usable data. What this lecture mainly got into was the design of accurate gyroscopes, which are a type of MEMS sensor, and accelerometers for use in IMUs. This lecture, in my opinion, went into much deeper depth about gyroscopes, so that is the topic I will present today. The reason I'm interested in this is my interests in avionics and embedded design. IMUs are invaluable in all types of avionics for determining where an airplane is, or a drone is, or a rocket is electronically, and knowing how these sensors work and getting a bit greater respect of how to treat them and how they become accurate and inaccurate, I feel are going to be useful for me in the future. So the idea that was covered is the idea of accurate capacitive gyroscopes in silicon. The way these gyroscopes work in silicon is there's a disk, and a really small, really thin disk surrounded by a capacitive ring with a bunch of individual sensors. The oscillating disk is applied a vibration. This vibration oscillates in the disk and vibrates around it. And then there's a different frequency that can be sensed, and this is sensed during using other capacitors on the capacitive ring. And using the difference between the supplied vibration and the sensed vibration can determine whether or not the gyroscope is rotating. The reason this works is because it was shown clear in the video, but unfortunately I have to deal with a picture, that when vibrating there are two different modes given. When stationary, the disc will vibrate up and down, exaggerate in the left side of the picture below, above the 0 degree axis, and it'll vibrate up and down in this position. During rotation, it will then vibrate up and down similarly at the same frequency, given that the drive and sense frequencies are the same, but instead of vibrating directly up and down, it'll be tilted at an angle, in this case 45 degrees. And by detecting this angle and the strength of the vibration from this angle, you can determine not only if something is spinning, but how fast it is spinning. There's a lot of ways that error can creep in during this measurement. For example, noisy environments are a really big deal, because the reason you detect a result is through vibration, but if your environment is vibrative itself, then it can create a false rotation and can throw a whole bunch of error in the works. So in regular industrial environments, these gyroscopes are kind of vulnerable. There's also damping, which can be induced, which can create frequency errors, because the frequency induced will not be the same as what is predicted, and also the sensing frequency might also drift off and might lead to some inaccuracies for measuring whether or not this gyroscope is actually drifting. Some of the frequencies can be thermal damping, which can come from inconsistencies in the way the disk conducts heat away from little spots within itself, and inconsistencies in the material itself, which can propagate around and cause damping as the resonance of the oscilloscope tries to propagate through and be sensed. There's also thin film damping, which is the property of it being extremely thin and having a lot of interactions with the holdings around the oscilloscope, which can increase damping further. This thinner film also does lead to a higher frequency, so is considered a desirable trait, but it does lead to some damping. Into my further research, I wanted to look into inductive gyroscopes. I assumed if there were capacitive gyroscopes, then there were probably inductive gyroscopes, and indeed there are. These gyroscopes seem to be better at dirtier environments, and because of their larger coil diameters and the ability to sense bigger materials, but they're also worse at smaller targets, smaller packaging, because of the way capacitors can detect a much smaller area, because inductors tend to propagate outside of themselves, as we have seen in physics, more than capacitors, which go from plate to plate.